Uh, what's going on, guys? So, everybody's having trouble connecting to either Schoology and or Zoom today. So what I'm doing is just going to go through what I wanted to talk about today with you guys, and then I'll post it as a video on Schoology. If you're watching it, you've found it already. And you guys just check this out and follow through with the notes. I would suggest copying down what we're going through or what I'm going through so that you have it. But this will be our class for today, if you will. All right, so let me go ahead and do this. So what I really wanted to do, I think I want to make some changes to what we kind of did last class to make things a little bit easier for ourselves, right? We were looking at the constant acceleration equations. Constant acceleration equations. And I don't want to change everything, but there's one thing that I think we can change to make this a little bit easier. We introduced the variables, right? We had xf or xi, xf, vi, vf, a, and t, right, as our variables. And we defined all of them, right? Initial position, final position, initial velocity, final velocity, acceleration, and time, right? We established all of those variables, and then we use those variables in our equations. But what I want to do is replace xi and xf with the variable delta x, which is displacement. So we can take our equations and simplify them, right, by incorporating delta x as opposed to xi and xf, right? Xi is initial position, xf is final position. But if we replace them with displacement, right, we can replace it with just the total distance or basically how far the object has traveled, right? Displacement is how far. Right? We can replace it with displacement, and then we can, instead of having to worry about two variables there, just worry about one variable, which stands for how far the object has traveled. Instead of object started here, object ended here, we can just talk about, well, how far did it go? And I think that simplifies our equations a little bit to make these four constant acceleration equations a little bit easier. So now I'm going to go back and I'm going to show you what our equations did look like, and then show you what they look like with displacement as opposed to initial position and final position, right? And it only changes three of the equations. It doesn't change every equation, but it will make, I think, three of the equations a little bit easier for us. So we have the constant acceleration equations, and we had four of them, right? We had equation number one, which was VF equals VI plus A times T. This one doesn't change at all because of our delta X, right? There was no XF or XI in this equation. So this one is the one that doesn't change a lot. But the other three will change. So originally, I had our second equation as, I think, XF equals XI plus VIT plus 1/2 AT squared. All right, so we're going to replace this, right, and make it a little bit easier And we're going to say that delta x equals VIT plus 1/2 AT squared, right? Delta x now, so instead of XF equals XI plus VIT plus 1/2 AT squared, we're just going to have delta x equals VIT, VI, initial velocity times time, times 1/2 A times time squared, right? So let me make sure that we know this is multiplication. VI times T plus 1/2 times A times T squared. So I think it simplifies it a little bit, right? We take two variables and we replace it with one variable. I think this becomes a little bit easier as the second equation. Third equation changes as well. The third equation, we had VF squared equals VI squared plus 2 times A times XF minus XI. All right, and this one we're going to replace as well, so that we have VF squared equals VI squared plus 2 times A times delta X, right? So instead of XF minus XI, we're just going to use delta X, right? Again, we change this from needing two separate variables to only needing one variable. I think it makes it a little bit easier, right? So this is what we'll use for equation 3. And then the last one, I forget even how I wrote this one, but I think I wrote it XF equals XI plus VI plus VF over 2 times T, right? I think that's how I wrote it. We are going to replace that one so that it says delta X equals VF plus VI over 2 times T. Right, so our three equations, they just change a little bit. And I think we substitute out two variables, replace them with one variable. It makes it a little bit easier for us. Again, we still want to follow the kind of rules that we established for when to use each equation, right? We use the first equation when distance isn't mentioned. We use the second equation when final velocity isn't mentioned. We use the third equation when time isn't mentioned. And we use the last one when acceleration isn't mentioned. Okay, so there are our four equations. We're just adjusting them a little bit to replace XF and XI with delta X, which I think makes this a little bit easier for us. Okay, so now let's do some example problems. All right, I think we did example problems of problem number, or we did example problems using equation number 1 and equation number 2. So we'll look at some example problems that use equation number 3 and equation number 4 today. All right, so let's see which one gives me what I want. That's equation 2. That's not what I want. I want equation number 3. Okay, I think I found it. All right. Let's put some text in here. Excuse me. A boat moves slowly inside a marina. And I think we started with we used something very similar like to this for the second equation. It throttled with an initial velocity of 1.50 meters per second. It speeds up with a constant acceleration. Actually, it speeds up, we'll say, to a velocity of 13.5 meters per second over 5 seconds. What was the distance? Or I guess I should say, how far did the boat travel while it was speeding up? So we have a boat, it's traveling at 1.5 meters per second. And then all of a sudden it tries to change speed, right? And it goes from speed of 1.5 meters per second to a speed of 13.5 meters per second over a 5-second time interval. And we want to know how far did the boat travel while it was speeding up. All right, so we looked at this last time, or we looked at how to go about solving these problems last time. And the first thing I like to do is make a table. All right, a table that includes all the variables that we might need. To solve the problem. All right, so we're going to have 2 columns, 1 column for the variable, 1 column for the value. And we have delta x, vi, vf, a, and t. All right. Now, obviously, my lines are terrible. So let's fix those a little bit. Delete that. Delete that. That's fine. Let's make this a little bit straighter. Make this a little bit straighter. Make the gaps a little bit more even. Okay, so like I said, we did this last time. We had the variable and the value. But last time we were working with XF and XI. This time, right, like I said, I think this is a little bit easier if we go ahead and just replace XF and XI with delta X, and delta X stands for how far the boat travels. So we have delta X, we have VI, we have VF, we have A, and we have T, right? So I set up my table. Now I'm going to go through the problem and pick out what I think is important, right? Initial velocity of 1.5, speeds up to a velocity of 13.5 over 5 seconds. And our question is, how far did the boat go? Okay, so if I look at plugging things in here, right? Initial velocity, 1.5. So my VI, I can put in 1.5 meters per second. Check that one off, I used it. Speeds up to a velocity of 13.5. So it accelerated and it reached a velocity of 13.5. So the final velocity, right, the ending velocity here is going to be 13.5 meters per second, right? So I can check that off. I use that one. 5 seconds, that's obviously going to be a time. So I can check that off. And our question is how far, right? We want to know how far. Now, how far is distance or displacement, which is delta X. So this is what I'm looking for. All right, so the variable that's not mentioned, right, doesn't show up in the problem is acceleration. So I'm going to cross acceleration out, and I'm going to use the equation that doesn't mention acceleration, which, if we look back, is equation number 4. Equation number 4 doesn't mention acceleration. And equation number 4, our rewritten version, says that delta x is equal to vi plus vf over 2 times t. All right, and then we can go ahead, we plug in our values, and we solve the equation. So delta x is our unknown. We don't know what that is, so we'll leave that as delta x. Vi is 1.5, so I can put in 1.5 for Vi, plus 13.5 for Vf, divided by 2 times t we said was 5. All right, so parentheses, exponents, multiplication, division. We actually, right, because this part is in the denominator, we actually end up having to do this part first. And we could put this in parentheses, right, those VF plus, or VI plus VF, to make that a little bit more apparent, right? The parentheses is what needs to go first. So we're going to add those two first. So we'll get delta x equals 1.5 plus 13.5 is 15 divided by 2 times 5. We take 15 divided by 2, I think we get 7.5. Yeah, 7.5 times 5. And 7.5 times 5, let me get out my calculator. 7.5 times 5 gives me 37.5. meters as the distance traveled by the boat. So there's an example using equation number 4, right? We used equation number 4 to solve that one. All right. Right, that was equation number 4. Yes, that was equation number 4. The last one is equation number 3. So let's do an example for equation number 3. I'm going to save this so I can post that later if I want to. Clear all my drawings, and let's do equation number 3, or a problem that involves equation number 3. I think this one does. Yes, it does. So a park ranger driving on a back road suddenly sees a deer 20 meters ahead. The ranger, who has an initial velocity of 11.4 meters per second, applies the brakes and slows with an acceleration of 3.8, negative 3.8. Oh, I clicked off the box. All right, good. Let me keep typing. 3.8 meters per second squared. How much distance is required? Or I guess we should say, how far does the ranger travel before they come to a stop? Okay, so here's our problem. Right, park ranger driving on a back road sees a deer 20 meters ahead. Initial velocity of 11.4, applies the brakes, slows with an acceleration of negative 3.8 meters per second squared. How far does the ranger travel before they come to a stop? So I'm going to set up my chart again so that I can write down my knowns and unknowns. I'm going to do this one quick. as opposed to making it super neat. So we have delta x, vi, vf, a, and t. Not worrying about neatness here. We have a spot for our variables. We have a spot for our values. We have our 1, 2, 3, 4, 5 variables. That VF wasn't very good. I just erased the entire problem. All right, I fixed it. All right, so now I read through the problem and I highlight what I think is going to be important. So 20 meters ahead, maybe be important. Ranger who has initial velocity of 11.4 meters per second, slows with an acceleration of negative 3.8. And we want to know how far does the Ranger travel? Okay, so, right, let's look at some of this stuff, see what we can include or what we maybe shouldn't include. All right. Park Ranger sees a deer 20 meters ahead. Now, I'm going to put this on the outside here, and you'll see why in a second, right? Because it is a distance. It's a displacement, right? The deer is 20 meters ahead. But we'll talk about why I put that on the outside as opposed to actually using that as a value. Initial velocity of 11.4. So I can put in here 11.4 meters per second. Applies the brakes, slows with an acceleration of negative 3.8. So A is negative 3.8 meters per second squared. We want to know how far does the Ranger travel? So this is why I put the 20 on the outside, right? Because the 20, delta x is how far the object that we're talking about travels, right? So the 20 meters is how far away the deer is. It's not how far the Ranger traveled. All right. So when our question is how far does the Ranger travel, that our delta x is what we're looking for, right? Just because the deer is 20 meters ahead doesn't mean that the car has to go 20 meters, right? The car could go less and not hit the deer, or the car could go more and unfortunately hit the deer. So the 20 meters is kind of a misnomer here. It's a number that's included, but it doesn't actually belong in the problem. All right. Well, notice here, we're still missing two things though, right? We're missing final velocity and we're missing time. So we haven't narrowed it down enough to actually pick the correct equation. We need one more thing. All right. And it actually comes from this end of the paragraph here, come to a stop, right? If our car is coming to a stop, and this is one of these things that we have to look out for because it's not super obvious, right? But it's part of the problem. If we come to a stop, that means our final velocity is 0, right? It doesn't come out and say that the final velocity is 0, but because it says it comes to a stop, that means our final velocity is 0. Now that leaves us finally with one thing that's not mentioned. Time isn't mentioned, so we'll cross out time. We have to pick the equation that doesn't mention time. I think the equation that doesn't mention time is equation number 3, which is VF squared equals VI squared plus 2A delta X, 2 times acceleration times the distance. And now we have to plug in and we have to solve our equation. So VF is 0, so I'll put in a 0 here, equals VI was 11.4, so 11.4 squared plus 2 times negative 3.8 times delta X is what we're looking for. So that stays as a delta X. And I have to now solve for delta X. So 0 squared is going to be 0. 11.4 squared gives me 129.96 plus 2 times negative 3.8 times delta X. Well, we can do the 2 times the negative 3.8. 2 times negative 3.8 is negative 7.6 times delta x. And now we have to use some problem solving skills to solve for delta x, right? Because it's not by itself originally. We have to get it by itself. First thing we're going to do is subtract 129 from both sides. So we get negative 100. These cancel. We get negative 129.96. Oops, that says 69. Equals negative 7.6 times delta x. Then we have to divide by negative 7.6 on both sides to cancel this out. So I'm going to divide both sides by negative 7.6. And 129, negative 129.96 divided by 7.6 will give us 17.1 meters is our delta x value. Delta x is 17.1 meters, which means, is the deer okay? Yes, the deer is okay because the deer is 20 meters ahead. We stopped 2.9 meters before we reached the deer. All right, so the deer survives in this one. Whew, we made it. All right, so just two final example problems for us that use equation number 4 and equation number 3. Some slight changes to our equations to make sure that we actually it's just to make it a little bit easier for us. There's not really a huge purpose for changing the equations around besides the fact that we want to make it excuse me, a little bit easier for ourselves. All right, so that is it for today. Thank you for checking that out. I will get this posted in a jiffy. If you're reading it already, then it's already posted, or you're watching the video, then it's already posted. I will see you guys on Friday.